Welcome to Huberman Lab Essentials, where we revisit past episodes for the most potent and actionable science-based tools for mental health, physical health, and performance. I'm Andrew Huberman, and I'm a professor of neurobiology and ophthalmology at Stanford School of Medicine. And now for my discussion with Dr. Eddie Chang. Eddie, welcome.
Hi, Andrew.
Great to be here with you. Your main focus these days is the neurobiology of speech and language. So for those that aren't familiar, could you please distinguish for us speech versus language in terms of whether or not different brain areas control them? When I think about language, I think about words and just talking. If I sit down to do a long podcast or I think about asking you a question, I don't even think about the words I want to say very much. I mean, I have to think about them a little bit, one would hope, but I don't think about individual syllables unless I'm trying to, accent something, or it's a word that I have a particular difficulty saying, or I want to change the cadence, etc. So what in the world is contained in these brain areas? What is represented? To me is perhaps one of the most interesting questions, and I know this lands square in your wheelhouse.
Sure. Let's get into this, Andrew, because this is one of the most exciting stuff that's happening right now, is understanding how the brain processes these exact questions. And speech corresponds to the communication signal. It corresponds to me moving my mouth and my vocal tract to generate words. And you're hearing these as an auditory signal. Language is something much broader. So it refers to what you're extracting from the words that I'm saying. We call that pragmatics, and sort of, are you getting the gist of what I'm saying? There's another aspect of it that we call semantics. Do you understand the meaning of these words and the sentences? There's another part that we call syntax, which refers to how the words are assembled in a grammatical form. So those are all really critical parts of language. And speech is just one form of language. There's many other forms like sign language, reading. Those are all important modalities for reading. Our research really focuses on this area that we're calling speech. Again, the production of this audio signal, which you can't see, but your microphones are picking up. There are these vibrations in the air that are created by my vocal tract that are picked up by the microphone in the case of this recording, but also picked up by the sensors in your ear. The very tiny vibrations in your ear are picking that up and translating that into electrical activity. It's such a complex feat. Some people would say it's the most complex motor thing that we do as a species is this speaking, not the extreme feats of acrobatics or athleticism, but speaking.
Well, and especially when one observes, opera or people who, freestyle rappers, and of course it's not just the lips, it's the tongue.
Yeah.
And you've mentioned two other structures, pharynx and larynx are the main ones that can you tell us, just educate us at a superficial level, what the pharynx and larynx do differentially? Because I think most people aren't going to be familiar with
sure.
that.
I'll talk primarily about the larynx here for a second, which is that if you think about when we're speaking, really what we're doing is we're shaping the breath. So even before you get to the larynx, you got to start with the expiration. We fill up our lungs and then we push the air out. That's a normal part of breathing. What is really amazing about speech and language is that we evolved to take advantage of that normal physiologic thing at a larynx. And what the larynx does is that when you're exhaling, it brings the vocal folds together. Some people call them vocal cords. They're not really cords, they're really vocal folds. They're two pieces of tissue that come together, and a muscle brings them together. And then what happens is when the air comes through the vocal folds, when they're together, they vibrate at really high frequencies, like 100 to 200 hertz. And the reason why men and women generally have different voice qualities is it has to do with the size of the larynx and the shape of it. Okay, so in general, men have a larger voice box or larynx, and the vibrating frequency, the resonance frequency of the vocal folds when the air comes through them is about 100 hertz for men and about 200 for women. So you take a breath in. As the air is coming out, the vocal folds come together and the air goes through. That creates the sound of the voice that we call voicing. It's not just your voice characteristic, it's the energy of your voice. It's coming from the larynx there. It's a noise. And then it's the source of the voice. And then what happens is that energy, that sound, goes up through the parts of the vocal tract, like the pharynx, into the oral cavity, which is your mouth and your tongue and your lips. And what those things are doing is that they're shaping the air in particular ways that create consonants and vowels. That's what I mean by shaping the breath. It just starts with this exhalation. You generate the voice in the larynx, and then everything above the larynx is moving around, just like the way my mouth is doing right now, to shape that air into particular patterns that you can hear as words.
Immediately makes me wonder about more primitive or non-learned vocalizations like crying or laughter. Are those produced by the language areas, or do they have their own unique neural structures?
We call those vocalizations. A vocalization is basically where someone can create a sound like a cry or a moan, that kind of sound. And it also involves the exhalation of air. It also involves some phonation at the level of the larynx where the vocal folds come together to create that audible sound. But it turns out that those are actually different areas. So people who have injuries in the speech and language areas oftentimes can still moan, they can still vocalize. And it is a different part of the brain. I would say an area that even non-human primates have that can be specialized, for vocalization. It's a different form of communication than words, for example.
Speaking of storage of and ability to speak, you are doing some amazing work and have achieved some pretty incredible, well-deserved recognition for your work in bringing language out of paralyzed people, essentially allowing people who are locked into a paralyzed state or otherwise unable to articulate speech using brain-machine interface, essentially translating the neural activity of areas of the brain that would produce speech into hardware, artificial, non-biological tools in order to allow paralyzed people to communicate.
So there are a series of conditions. They include things like brainstem stroke. The brainstem is the part of the brain that connects the cerebrum, which is the top part, does our thinking and a lot of the motor control, speech, language, everything. And the brainstem is what connects that to the spinal cord and the nerves that go out to the face and vocal tract. So if you have a stroke there, you could be thinking all the wild, creative, intelligent thoughts you have in the mind and the cerebrum, but you can't get them out into words, or you can't get them out to your hand to write them down. So that's a very severe form of paralysis called brainstem stroke. There's another kind of conditions that we call neurodegenerative, where the nerve cells die, basically, or atrophy in a condition called ALS. That's a very severe form of paralysis. In its extreme form, people essentially lose all voluntary movement. The muscles to their diaphragm and their lungs essentially give out as well. They get weakness there, and then they can't breathe anymore. In our field, these are kind of like the most devastating things that can happen. This condition of what we call being locked in refers to this idea that you can have completely intact cognition and awareness, but have no way to express that. No voluntary movement, no ability to speak. And that is devastating because psychologically and socially, you're completely isolated. That's what we call locked-in syndrome. And it's devastating. So we've been studying this patterning of electrical activity for consonants and vowels. And essentially, once we figured out a lot of these codes for the individual phonetic elements, part of the lab started to focus on this very specific question. For people who have these kind of paralysis, could we intercept those signals from the brain, the cerebral cortex, as someone is trying to say those words? And then can we intercept them and then have them taken out of the brain through wires to a computer that are going to interpret those signals and translate them into words? So we started a clinical trial. It's called the Bravo trial. It's still underway. And the first participant in the Bravo trial was a man who had been paralyzed for 15 years. He was in a car accident. He actually walked out of the hospital the day after that car accident, but the next day had a complication related to it where he had a very large stroke in the brainstem. And that turned out to be devastating. He didn't wake up from that stroke for about a week. He was in a coma for about a week. And when he woke up from that coma, he realized that he couldn't speak or move his arms or legs. As he told me or communicated to us, that was absolutely devastating. He wanted really to die at that time.
Could he blink his eyes or move his mouth in any way?
He could blink his eyes. He had some limited mouth movements, but couldn't produce any intelligible speech. It was like completely slurred and incomprehensible. He survived this injury. A lot of people who have that kind of stroke just don't survive. The way he actually communicates, because he has a little bit of residual neck movements, is that he improvised and had his friends basically put a stick attached to his baseball cap. And because he could move his neck, he would essentially type out letters on a keyboard screen to get out words. In fact, this is how he communicated, was through a device that he would essentially peck out letters one by moving his neck to control this stick attached to his baseball cap. He hadn't really spoken for about 15 years.
Oh, goodness.
Yeah. So it was part of a clinical trial. It was, something that our hospital and also the FDA, had to approve and looked at very carefully. But given a lot of the work that we had done, there was some basis for why this might work. And so we did a surgery where we implanted electrodes onto these areas that control the vocal tract, the areas that control the larynx, the areas that control the lips and tongue and jaw movements when we normally speak. These are areas that presumably may be active. That was our hope. And he underwent a surgery, a brain surgery. We put an electrode array and we connected it to a port that was screwed to his skull. And the port actually goes through his scalp. And he's lived with this now for the last 3 years. So he has an electrode array that's implanted over the part of his brain that's important for speech. It's connected to a port. And then we connect a wire to that port that translates those, what we call analog, brain waves, and converts them into digital signals. We put them through machine learning or artificial intelligence algorithm that can pick up these very, very subtle patterns. You can't actually see them with your eye in the brain activity and translate those into words. And this is something that took weeks to train the algorithm to interpret it correctly. But what was incredible about it was to see how he reacted. He would be prompted to say a given word, like, outside, for example. And then he would think about it, try to say it, and finally those words would appear on the screen. And what was really amazing about it was you could really tell that he got a kick out of that because, his body would shake in a way and his head would shake in a way that he would start to giggle. That was cool to see. But then I also realized that when he was giggling, it kind of screwed up the next word's decoding.
Is that a bug you've since fixed?
No, we haven't fixed that. It's easier just to tell him to stop giggling. The way this worked was we trained this computer to recognize 50 words. We started with a very small vocabulary that's expanding as we speak. I think that this is just a matter of time before these vocabularies become much, much larger. But we started with a 50 set of words. We created essentially all the possible sentences that you could generate from those 50 words. Why that was important was you can use all those possible sentences to create a computational model, computer model of all the different word combinations to give different sentences given those 50 words. And then you can essentially do what we call autocorrect. It's the same kind of thing that we do when you're texting, for example. You get the wrong letter in there. Your phone actually knows, because of its context, what to correct it. So because the decoding is not 100% correct all the time, in fact, it's far from that, it's really helpful to have these other features like autocorrect, the stuff that we use routinely now with texting that makes it correct and then updates it. So it's a combination of a lot of things. It's the AI that is translating those brain activity patterns, but it's also things that we've learned from speech and speech technologies that, you put all together and then all of a sudden it starts to work. That was the first time that someone was paralyzed and could create words and sentences that was just decoded from the brain activity.
These days, we hear a lot about Neuralink, right? Elon Musk's company. While brain-machine interface of the sort that you do and that other laboratories do has been going on for a long time, there's been some press around Neuralink about the promise of what brain-machine interface could do. What are your thoughts about manipulating neural circuitry to achieve suprahuman or superhuman or supraphysiological functions? And here we don't even have to think about Neuralink in particular. It's just but one example of companies and people in laboratories that are quite understandably considering all this.
It's a really interesting time right now. The science has been going on for decades. The work that we've done in this field that you call brain-machine interface has been going on for a while. And a lot of the early work was just trying to restore things like arm movement or having people or monkeys control a computer cursor, for example, on a screen. That's been going on for decades. What's been really new is that industry is now involved and some of this is now becoming commercialized. And we're starting to see us now cross over to this field where it's no longer just research, that we're talking about medical products that are designed to be, surgically implanted. In some cases, there's people doing this kind of work non-invasively as well. They don't require surgery. The specific question that you were asking about is an area that we call augmentation. So can you build a device that essentially enhances someone's ability beyond supranormal, super memory, super communication speeds beyond speech, for example, superior precision athletic abilities? I think that these are very serious kind of questions to be asking now because, as you mentioned, the pathway so far is really to focus on these medical applications. I personally don't think that we've thought enough, actually, about what these kind of scenarios are going to look like. And I don't think we've thought through all the ethical implications of what this means for augmentation in particular. There's part of this that is not new at all. Humans throughout history have been doing things to augment our function. Coffee, nicotine, all kinds of medications that cross over from medical to consumer, that is everywhere. So the pursuit of augmentation or performance or enhancement is really not a new thing. The questions really, as they relate to neurotechnologies, for example, have to do with the invasive nature. For example, if these technologies require surgery, for example, to do something that is not for a medical application, again, that is not exactly new territory either. People do that routinely for cosmetic kind of procedures, for physical appearance, not necessarily cognitive. So I do think that provided the technology continues to emerge the way that it does, that it's going to be around the corner. And it probably is not going to be in ways that are super obvious. I don't think it's going to be like, can we easily memorize every fact in the world? But in forms that are going to be much more incremental and maybe more subtle. In many ways, we already have that now. Like, for example, you don't have to have a neural interface embedded in your brain to get information, essentially access to all information in the world. You just have to have, your iPhone. Whether you could do it faster through a brain interface, I definitely wouldn't rule that out. But think about this, that the systems that we have already to speak and to communicate have evolved over, thousands and millions of years, and they're supported by neural structures that have bandwidth of millions of neurons. There's no technology that exists right now that people are thinking about that are in commercial form, certainly, not even in research labs, that come anywhere close to what has been evolved for those natural purposes. So I'm essentially saying two sides of this, which is we're already getting into this now. This is not new territory. This topic of augmentation, both physical and cognitive, we've already surpassed that. That's part of what humans do in general. But we are entering this area of enhanced cognition, these areas that I think the technology is going to be the rate limiting step and how far it can go. And we have not had the full conversations about, number one, is this what we actually want? Is this going to be good for society? Who gets access to this technology? These are all things that are going to become real world problems.
Could you tell us what you're doing in terms of merging the brain-machine interface with extraction of speech signals from people who are locked in, like Pancho, with facial expressions?
Sure, yeah. I'm here with you in person. We could have done this virtually, probably. It's pretty easy to do that. We could have recorded this really separate, but there is something about being able to actually see your expressions and to understand other forms of communication. So another really important one is nonverbal. the expressions that you're making. For example, if you have a quizzical look on your face, if I'm saying something not clear, that's a sign to me that I need to rephrase it or to say it in a different way or to slow down. Facial expressions actually are a really important part of the way we speak. And there's two things. It's not just the expressions of like how you're feeling and perceiving what I'm saying, but it's also seeing my mouth move. And your eyes actually see my mouth move and my jaw move in a particular way that actually allows you to hear those sounds better. So having both the visual information, but also the sounds go into your brain is going to improve the intelligibility, also make it more natural. And the reason why we're also very interested in this idea of not just having text on a screen, but essentially a fully computer animated face, like an avatar of the person's speech movements and their facial expressions, is going to be a more complete form of expression. Now, you can imagine right now, that might just be someone looking at a computer screen interpreting these signals. But I think the way things are going in the next couple of years, a lot more of our social interactions, more than even now, are going to move into this digital virtual space. Of course, most people are thinking about what that means for most consumers, but it also has really important implications for people who are disabled, right? And whether how are they going to participate in that? And so we were thinking really about, for people like Pancho and other people who are paralyzed, what other forms of BCI can we do in order to help improve their ability to communicate? So one is essentially building out more holistic avatars, things that can essentially decode, essentially their expressions or the movements associated with their mouth and jaw when they actually speak to improve that communication.
So do you envision a time not too long from now where instead of tweeting out something in text, my avatar I'll type it out, but my avatar will just say it. It'll be an image of my avatar saying whatever it is I happen to be tweeting at that moment.
That's what we're working on. That is going to happen, and it's going to happen soon. And there's a lot of progress in that. And again, we're just trying to enrich the field of communication expression to make it more normal. And we actually think that having that kind of avatar is a way of getting feedback to people learning how to speak through a speech neuroprosthetic. That's the device that we call it. It's a speech neuroprosthetic. That is going to be the way that can help people learn how to do it the quickest, not necessarily like trying to say words and having it come on a screen, but actually have people feel like it's part of themselves, or that they are directly controlling that illustration or animation.
I get a lot of questions about stutter. What can people with stutter do if they'd like to relieve their stutter? Stutter
is a condition where the words can't come out fluently. So you have all the ideas, you've got the language intact. Remember we talked about this distinction between language and speech. Stuttering is a problem of speech, right? So the ideas, the meanings, the grammar, it's all there in people stutter, but they can't get the words out fluently. So that's a speech condition. And in particular, it's a condition that affects articulation, specifically about controlling the production of words in this really coordinated kind of movements that have to happen in the vocal tract to produce fluent speech. And stuttering is a condition where people have a predisposition to it. So there's an aspect of stuttering, you are a stutterer or you're not a stutterer. But people who stutter don't stutter all the time either. So you could be a stutterer who stutters it sometimes, but not others. And really the main link between stuttering and anxiety is that anxiety can provoke it and make it worse. That's certainly true, but it's not necessarily caused by anxiety. It can essentially trigger it or make it worse, but it's not the cause of it per se. So the cause of it is still really not clear, but it does have to do with these kind of brain functions that we've been talking about earlier, which is that in order to produce normal fluent speech, we're not even conscious of what is going on in our mouths, in our larynx. We're not conscious, and if we were, we would not be able to speak because it's too complex, it's too precise. It's something that we have really developed the abilities to do, and we do it naturally, right? It's part of our programming and part of what we learn inherently, innate, it's just through exposure. So stuttering is essentially a breakdown at certain times in that machinery being able to work in a really coordinated way. You can think about, the operations of these areas that are controlling the vocal tract. Let's say speech is like a symphony. In order for it to come out normally, you've got to have not just one part, the larynx, but the lips, the jaw. They can't be doing their own thing. They have to be very, very precisely activated and very, very precisely controlled in a way to actually create words. And so in stuttering, there's a breakdown of that coordination.
If somebody has a stutter, is it better to address that early in life when there's still neuroplasticity is very robust? And if so, what's the typical route for treatment? I have to imagine it's not brain surgery typically. I'm guessing there are speech therapists that people can talk to and they can help them work out where they're getting stuck in the relationship to anxiety.
Yeah, exactly. I mean, part of it is about that anxiety, but a lot of it really has to do with therapy to sort of like work through and think of tricks basically sometimes to create conditions where you can actually get the words to come out. Some forms of stuttering are really initiation problems. Just getting started itself is very hard. You want to start with the initial vowel or consonant, but it won't emit. So a lot of that therapy is really just focusing on like, how do you create the conditions, for that to happen? There's another aspect to it that I find very interesting is that the feedback, essentially what we hear ourselves say, for example, every time that I say a word, I'm also hearing what I'm saying. So that's what we call auditory feedback. That turns out to be very important. And sometimes when you change that, it can actually change the amount someone stutters for better or for worse. And it's giving us a clue that the brain is not just focused on sending the commands out, but it's also possibly interacting with the part that is hearing the sounds. And there's something might be going on in that connection that breaks down when stuttering occurs. So there are individuals that are stutterers, but they don't stutter all the time. In those instances, there's something happening in those particular moments where this very, very precise coordination needs to happen in the brain in order to get the words out fluently.
Eddie, I have to say, from the first time we became friends, 38 years ago,
something
like that, to be sitting here with you today for me is an absolute thrill. Not just because we've been friends for that long or that we got reacquainted through literally the halls of medicine and science, but because I really do see what you're doing as really representing that front, absolute cutting edge of exploration and application. I mean, the story of Pancho is but one of your many patients that has derived tremendous benefit from your work. And now as a chair of a department, you of course work alongside individuals who are also doing incredible work in the spinal cord, et cetera. So on behalf of myself and everyone listening, I just really want to thank you for joining us today to share this information, but also just for the work you do. It's truly spectacular. So thank you ever so much.
Thanks.